Hello, I welcome you guys to our sixth lecture. And in regards to what we've been doing so far, um, basically we've been trying to look at how to calculate the amount of reinforcement which is needed, or the area of reinforcement which is needed for the longitudinal rebars, right? So that if we have um, a beam, assuming that these are the columns. Okay, so the columns are somewhere here. It typically means that we are looking at the rebars, right? So normally this would be the compression steel. Then here we have the tension. Okay. I mean, this is a typical simply supported structure, right? And the goal of these steel that we have is to prevent pretty much bending failure. All right. So that's the general idea, right? Because concrete has very good compressive strength, but then low tensile strength. So placing the rebars in there is able to, through um, the bond action, is able to help prevent or mitigate the effect of tensile failure or the likelihood of tensile failure occurring. But then tensile failure or bending failure is not the only kind of failure that a being can experience, right? So sometimes if you have a beam and you have, let's say, series of loads, let's say in this case, concentrated loads on the beam, if the shear coming from these loads, so if the shear, let's say the shear forces, all right, if the shear forces exceed the shear capacity of the beam will fail, okay, or the beam is likely to fail. All right. But this kind of failure is termed as shear failure. Okay. There's a more appropriate word which we'll look at later, but in simple terms, shear failure. All right. So usually if you have a beam, let me do it in three and two dimensions, sorry, and you have some supports at the ends. So these are the supports. Depending on the magnitude of the load, you usually would have the beam failing along this end. Okay. For bending failure, it's usually at midspan. Okay. That's where the tensile cracks typically formed. But for shear failure, the failure occurs closer to the supports, right, in a diagonal format, typically. All right. So with that, we need to come up with some system or some arrangement of rebars which can then help to prevent the occurrence of this shear failure, right? So for that matter, we need to understand what shear is. Okay. Pretty much everything that has to do with shear when it comes to a typical beam design, right? So let's go through the beam analogy. what happens is that um, if let's say this could be your, let me draw the support, sorry. Uh, Draw support here. Okay, these are column columns in a way. Normally, when you have this will be your compress, like when you have a beam, it either goes both compression and tension, right? So depending on the load, this could be your compression, right, behavior, more or less. Okay, this is the compression, and then this will be the tensile. Okay. And then usually closer to the supports, okay, closer to the supports, you would realize that these principal, so let me put it here, this principal stresses, right, which are typically either compressive or tensile. Okay, these stresses are inclined, okay, and steeper when we get close to the supports. Okay, and then again, or if we've realized anytime we draw shear forces, we realize that shear forces close to supports are typically high. Let me say are usually high, which means that if the structure is going to experience high shear forces, they are likely to occur closer to the supports. All right. So because of the sorry, because of the arrangement of the tensor or the position of the tensor stresses towards the support, these tensor stresses closer to supports will cause diagonal cracks, will typically cause diagonal cracks. Okay. Um, and these cracks, they tend to develop rapidly. Okay. And this is the reason why we when it comes to design, we are very critical about the shear because when you compare shear to bending, bending is typically gradual, especially when you have designed your beam for the rebars to yield first. The bending failure is gradual. But with shear, regardless of whether you have the longitudinal rebars in there or not, it can be quite abrupt or it can develop rapidly, which means that um, failure can be sudden. All right. And we do want to avoid such catastrophic sudden failure. Right. Um, so, for example, okay, we have two main, let me talk about the two main types of failure and the shear, and then we can look at which one we tend to go with a lot. All right. So let me see types of failure with regards to shear. Okay. The most common, because of the code limitations, has to do with what we call diagonal um, tension failure. Okay. So with that, I'm just gonna draw half a beam. Okay. So you have a beam here with some supports, okay, and then um, some loads at some distance away from the support. All right. So under such failure mode, your crack direction is in this form. It's usually from the face of the support towards the load point. All right. Um, so let me put it this way. This type of failure occurs between the face of the support and the load point. All right. So typically, if this is a concentrated load, then it's easier to determine the path of your diagonal failure, right? So normally what this means is that if the tensile stresses, all right, which can be developed from the shear forces, if they exceed the tensile capacity, which we know to be quite small for concrete, it means that we need to what's the name? Provide some reinforcement, right? So provide reinforcement. And this type of reinforcements I usually will call links. So some say links or some say stirrups. All right. They are typically vertical members we place um, in the beam to help prevent shear failure. All right. So the tensile capacity of the concrete. Let me add that. Okay. Normally, it's not only the concrete. There are three modes that add up to the tensile strength of the concrete. We'll look at that shortly. But normally, we say that if the tensile stress, which is coming from the load, exceed that of the tensile capacity of the concrete, then it means that we need to provide some form of reinforcement. Okay, and that's reinforcement, which normally we call them shear links. Okay, so let me just put a shear in front. Hopefully, I have space for that. This is terrible. So it's called shear links or stirrups, right? I think links seems to be the more common word being used, right? So that's the first form of, all right, which we tend to experience a lot. Now, the next form of failure that likely to happen uh, is what we call the diagonal compression failure. So again, you have your structure, uh, you have your support, all right. Then you have your load, again, some distance away. You will have some failure mode on this end, okay? But typically, this will be in compression. And why do we have this kind of failure? And this occurs when we have very large shear forces, okay, which are coming from the loads, okay. So these large shear forces, which are near the support, they typically lead to crashing of the concrete, okay, crashing of the concrete. So anytime concrete is crashing, then it means that it's undergoing compression. All right. Normally there's some limitations in the code to avoid this kind of failure. And to avoid this kind of failure, we just say that the maximum shear stress in the beam should not exceed a certain value. All right. So it should not, maximum stress should not be greater than the lesser of either 5 newtons per millimeter squared or 0.8 square root of FCU. Okay. So the lesser of these two is what governs our designs. Okay. So the code stipulates that no matter what you do, the shear stress in your beam coming from the load should not exceed these values, so that at least uh, from the onset we avoid compression failure. All right, so that the only kind of failure we can tackle in this case would be diagonal tension failure. All right, so normally, so if there are no reinforcement to prevent the diagonal tension failure, how is the concrete or the reinforced concrete able to resist um, shear? All right. So so let me say shear resistance by reinforced concrete. Let me see. So reinforced concrete without shear links. Okay. And the resistance can be achieved by three. I think I mentioned there are three main ways by which we can provide that resistance. Can be achieved, or another way to put it is that the shear in the beam, or we can put this maybe the shear in the beam is carried by these three items. So one is the, oops. So one is the concrete in the compression zone. Okay, so that provides uh, some capacity towards resisting the uh, shear stresses that are coming onto the beam. The other one would be what we call the doweling action. All right. And that has to come from the tensile reinforcement. Okay. So this tensile reinforcement is a longitudinal reinforcement. All right. So when you find your AS, that AS that you find, and then you place your rebars at the base or at the bottom side, that rebar can also be able to carry some of the tensile stresses, or can be able to resist some of the tensile stresses. All right. And it's able to achieve that primarily through the bond between the concrete and then the rebar. Okay. And that's like a good bond is critical when it comes to reinforced concrete. Right. The third one has to do with the aggregate interlock action. Okay. So this has to do with the stones and then the sand, how they are interlocked together. That also provides some resistance against the what's that name? The shear. All right. So if after all of these, so the concrete and compression, the bond between concrete and rebar, and also the aggregate lock, if all of these is still not adequate to carry the shear stresses coming onto the beam in this case, then we need to provide the shear links. All right. So let's understand the shear links, right? Let's understand how we come about, and then also look at some equations that can be used to um, 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 calculate the area of shear that we need, and also the spacing of the shear links that we need. Okay. So now let's look at sometimes you want to label this nicely. So let me call this this whole place, let me call it A. Okay. Let me call this guy here B. Let me call this C. Then I can call this D. Okay. Where D we're looking at the shear links itself. Okay. Or to bracket the stirrups. The way concrete behaves when you have stirrups in there is similar to a truss. Okay. So let's say I have this huge concrete beam. So I have the um, the column as support. Then I have my main rebar. So there's the top and there's a bottom rebar. Okay. Then here, these are my stirrups. Okay. So to derive the equation, we initially assume that the stirrups are placed at a distance D, right? Where D, we know D to be what? The effective depth. So usually that same D can also be put here. Let me change the color so that it makes some sense to us. So this is D again, all right, as we are used to, all right. And then we have at this point the shear force V, or the shear or the reaction V, all right, which is pretty much how we calculate our shear force. Okay. Um, so usually when you're looking at the stirrups, it uses the truss analogy. So let's say, let me put here, let's use analogy to represent the shear in the beam. Okay. So a few things to note. The vertical members in a truss, or in this particular truss, are the stirrups, okay, which are the green line that I've just drawn. Are the stirrups. And then the bottom chords are the tensor, or what we call the longitudinal reinforcements, all right, so that anytime I use them, they're pretty much the same. Okay. Then, so the concrete itself, will act as the diagonal, which I'm here to show, act as a diagonal, and then top chords. Okay. So this could be the diagonal in there. Okay. And then the top chord, because it's not always that we have compression reinforcement, right? So the top portion of our truss will be governed by uh, the concrete, right? The concrete in compression. Remember, we have to remember that we mentioned that the shear can also be carried by the concrete in the compression zone. All right. So the top part in this case here will be part of the compression zone. Okay. All right. So typically this angle here, theta theta or theta here, they are typically, so theta is typically 45 degrees or close to 45 degrees. Okay. And this has been proved through experiments that normally this angle is close to uh, uh, um, 45 degrees. And this also agrees, I think the G is only one. This also agrees with, so let's put here, agrees with the cracking direction of beams close to the supports. Okay. So I think if you look at it, if you go up there to the tension, the diagonal tension failure, normally this angle here, theta, is almost 45, almost all the time. It could vary a little bit, but then through experiment and all of that, the angle here or the crack angle can be around 45 degrees. All right. So let's say let's put a few things together. Let's so let's say that the area, oh, still the same color. The area of what's the name? Stirrups needed. So the cross-sectional area. So this be cross-section. We'll look at what these things are, what legs mean. Okay, we'll look at it shortly. Let me underline that. FYV or F subscript YV is the characteristic strength of the stirrups rebar. Okay. And then we have V being the shear force. Okay. So the shear force due to the ultimate load. All right. So here means that we would have factored the loads, have a 1.4 for dead loads and 1.6 for live loads and all of that. Okay. So let's just take note of that. So if we take a section through this, let's just take a section like that. Take a section through this. Let's call this section XX. All right. So normally if you use the method of sections, I'm not going to spend too much time on this. But if you use the method of sections from the truss analysis, you would realize that the shear force V will be equal to 0.87 FYV ASV. So the shear force is going to be the area of the rebar times 8 strength, which is force, right? The 0.7 has to be the partial factor of safety. All right. And then the average shear stress, small v, is the shear force at any point divided by the width times the effective depth. All right. So this is what we call the average shear stress. Okay. And this could be in the section. So any point in the section. All right. All right. So it could be at the support at some distance away from the support, which means that what is going to change would be the shear force. So the shear force at different points on the structure will give you varying shear stresses. All right. So this is just the general equation for finding the shear stress. Okay. So we can compare the two equations, equation 1 and then equation 2. I can rewrite equation 2 so that the shear force is the subject, and this becomes V. Yeah, the V looks like F, like S. So this one becomes V, small letter V, B. The big letter V is the shear force. The small letter V is the shear stress, right? So if I compare these two, then it means that 0.87 FYV ASV is equal to VBD. All right. And this equation is valid because, so here we are assuming that the stirrups are spaced at a distance D. So now the question is, what if they are not spaced at a distance D? Maybe the spacing of the stirrups they vary. It could be any distance. So let's call SV the spacing of the stirrup. So this spacing can be either D or at any other distance. Now, if that is the case, then we can rewrite the above equation to include that in there. So it becomes 0.87 FYV ASV and this will be equal to the shear stress VB times D times SV over D. So this SV over D is like a ratio. Oops. So this, why is it not selecting? Okay. So this SV over D is a ratio, right? And with this ratio, what it means is that if SV is equal to D, then this equation returns to what we have up there, right? Because they'll cancel each other, right? So here we have the general equation for the stresses. So we can do some bit of rearrangement again. So let's find a ratio of the area of the stirrups to the spacing, and that will give us VB over 0.87 FYV. Okay. But then at some point we mentioned that the concrete in itself has some shear capacity. All right. So bringing in stirrups more or less is going to add up, or it's going to augment the strength of the concrete so that the two of them can work together and then have enough shear capacity against what's the name, against the shear stress. All right. So if that is the case, then we need to modify So we need to modify this equation slightly. We need to modify the equation here so that we can, and the goal is how we can include, what's the name? Um, the fact that, what's the name? That concrete um, can resist some amount of shear. Okay. Otherwise, we'll have an over conservative design, which will not be advised. So let's have a new parameter, small letter VC. Let's call it the ultimate shear stress. Yeah, so small letter VC becomes the ultimate shear stress that can be resisted by the concrete. All right. And remember, this is not only the concrete, but the concrete's in the compression zone. The dual action of the rebar, the main rebar, the concrete, and also the aggregate interlock action or interlocking action. They all add up to provide some resistance against the shear. Okay. So it means that if that is the case, then the modification of, let me call this equation 4. So the modification of equation 4 would be that ASV over SV will be equal to B into brackets small v minus small vc all over 0.87 FYV. All right. And this here, it's needed to be able to determine the area of rebar needed for the shear. So there's usually a table. You go to the table. The table has the ASV over SV value. You pick one that is higher. There's also gives information as to what the spacing can be. Then with that, you can calculate the area of rebar needed for the stirrups. So let's look at the VC table, which is a very important table that we need to pay attention to. So in this space here has to do with, so this is our effective depth, D, right? And then the values in here, each one of them, whichever one we choose, gives us the VC, which is the concrete shear stress or the shear stress in the concrete, all right? So to find the VC, so to find VC, we need two parameters, all right? So we need the D, which is the effective depth. And we also need the percentage of the reinforcement, all right? So percentage of reinforcement, all right, at that section. So okay, and that percentage is what we call 100 AS over BD. So it's a ratio of the area of steel to the cross section of the concrete. So that a value divided by the total times 100%. So that's what this stands for. So once we have D, and then we have 100 AS over BD, we can determine the, what was that name? We can determine the, the, the VC, all right. Um, so you would realize a theme that for shallow members, okay, so those that have smaller d, so smaller d values, how do we spell values? Smaller d values. So for shallow members, and it would, and also for larger percentages, VC increases. So let's take note of that. And this has to do with the fact that once the area of tension shield is a lot, it means that it would add up to the concrete resistance. All right. So that's something to take note of. Okay, which means that we don't need too much extra stirrups to overcome the shear stress. All right. So we know the VC to be the shear stress. All right. The shear stress in the concrete. If you want to know the shear resistance of the concrete, all right. So the shear resistance of the concrete, let me call that VC, where VC is the shear resistance. Of the concrete. All right. So normally when we divide, or technically if we divide the shear resistance, let me put it this way. Let me change the color. If we divide the shear resistance by the cross-sectional area of the concrete, then we get the shear stress. Right. That's its basic terms. But then to find the total shear stress resistance, all right. The total shear stress resistance, for now, let me just put it here. What's wrong with my pen? Okay. So this is for the concrete. All these are for the concrete. Okay. So let me put one here for the stirrups. Before that, I write the total. So for the stirrups, so this is for concrete only. And then V, so big V here, which is equal to ASV over SV times 0.87 FYV times D. This will be the shear resistance for or of the lengths of the stirrups only. Right. Okay. So maybe I can call this one Sometimes you're careful how you name them because some of the naming you end up that you maybe you name this one VS, then later you're going to see a VS somewhere which means something entirely different. All right, so we just need to be careful with the naming process. Okay, so that if we want to find the total shear resistance, so pretty much it will be that of the concrete plus that of the stirrups. Okay. So that total shear resistance, I think is called Vn, if I'm correct. Vn here, big Vn, will be pretty much ASV. So let me call this one VS for now. All right. If there's any other VS along the line and it's different from this, I would explain. All right. So ASV, SV plus, sorry. So the plus is times uh, times 0.87 FYV plus BVC uh, into bracket times D. Okay. And this Vn also can be termed, it's used to also identify the nominal shear, which we'll look at again. All right. So this is for concrete and stirrups. So please take note of this equation. We will be seeing this equation a lot. Okay. We'll be seeing this equation and then this table here will be very useful. So let's say important. So important. Okay, and then what again do I have to show you guys? Yeah. So a few questions that are important to us. The same applies to this equation here also. Let me put here important. All right. So I would notify you of the important equations as we go along. Right. So again, I think we are still on the stirrups, eh? Okay. So let's look at a typical example of stirrups. Okay, maybe just how they look like, all right. In general, this is how stirrups look like. Okay. That if this is the outline of your concrete, then your stirrups have this, right, and then you have the rebar, sorry, you have the, so you have your longitudinal rebars sitting in there, all right, and then here, this here is the stirrups, okay. And how do we count them? So here is one leg, oops, different color. Okay, let me see if this works. Okay, great. So this is one leg. This is the second leg. This is one leg, another one leg. Okay, so in effect, it becomes two legs. Okay, and that's how come we call it two legs. In other cases, you could have this being your beam, and then your rebars could be maybe three, and just exaggerate a little bit. And you could have rebar arrangements like this. So this one has 4 legs. Okay, so this one has 4 legs. 1, 2, 3, 4. So here's 1, 2, 3, and 4. And the 4 legs would impact the area. All right, the area that we need. Okay. So let's just take a note of it. Um, Usually a few things about stirrups. So we are looking at stirrups. Stirrups should be, normally they should be close linked. So that's one. So like it should normally not be open. And then it should also make um, a rigid cage of the beam reinforcements. Uh, and again, all tension rebars must be enclosed by the links. Okay. Mhm. So when calculating for shear links, there just show this to you guys. Hopefully, um, looks like what's wrong with my screen? Okay, hopefully it picked. Yeah. Paste this here. Okay, great. All right. So when defining shear links or the area of shear links that we need, and also the number and what locations there are 3 conditions that we have to satisfy. Satisfy. Is the shear stress less than, or is the shear stress coming from the shear forces less than the shear stress of the concrete? Right. Is it less? Is it more? If it's less, is it less by how much? If it's more, is it by how much? All right. And that would inform us as to whether we need the reinforcement, shear reinforcement or not. Okay. So if you look at the first part right here, okay, if the shear stress is less than half of the concrete shear stress, then you don't need any stirrups. That's what the code says, right? So from table 7, BS 8110. So that's the first one. So usually when you are checking whether you need shear stress, stirrups or not, you need to define or go through these 3 checks and see whether which one would govern. All right. The second thing is to look at the fact that is the shear stress at that section more than half of the concrete shear stress, and then less than 0.4 plus the concrete shear stress. Okay. So we check. So we check this also. And then when we check, and then your shear stress lies within this range, then The code says that what we should provide what you call nominal. Nominal means just enough, minimum, all right? And if we are to provide nominal, then it means that um, so for 2, which is for nominal, where 0.5 VC is less than V is less than VC plus 0.4, then our ASV over SV should be greater than, right, or equal to 0.4B over 0.87 FYV. All right. So it's the same thing as we're written over here, but just that I just prefer it to be written in this form most of the time. Okay. Then the third case. All right. So the third case states that if our shear stress at a particular section is more than the concrete shear stress plus 0.4, then we need to do a proper design and provide shear links. All right. But again, the shear stress V should not exceed certain limits. The reason is that we want to prevent diagonal compression failure, as had mentioned earlier. And it's a reason why we have this here 0.8 FCU or 5 newtons per millimeter squared. Okay. Sometimes when I'm going through this, it looks like there's so much to learn, there's so much to do. But trust me, the steps are fairly straightforward. And after we are done all of this, we'll put together the steps and you'll see that it is fairly straightforward to design. One of the more difficult things to do with design, at least through my experience, is coming up with the loads and how the loads are being transferred from one structural member to the other. If you're able to grasp that one quite well, the design itself is more like a stepwise process, right? You can write an algorithm for the design that go like, okay, try step A. If step A doesn't work, maybe do step B. If step A works, do step C, and that kind of like procedure. All right. Okay. So take a note of it. Um, so let's see if we can look at some examples. I think there's one more table I need to show you, or I've already, okay, I think I have the table already showing it, so it's fine. And with stirrups, right, we are placing the stirrups at some spacing. So this space is what we call the SV. Okay. The code to the BS 8110 states that or recommends that our spacing should not exceed 0.75 the effective depth. Okay. So let's take a note of that. All right, it should not exceed 0.75 D. So whatever spacing that you choose for your effective depth, it should not exceed 0.75 D. Okay. Now let's play around with some examples. Just look at some examples and then we'll see. I think this table, the table I brought earlier, take note, this table only works for this table works for FCU equals 25 newtons per millimeter squared. All right. So now the question is, what if FCU is maybe 30 newtons per millimeter squared? The code stipulates that um, for other values of FCU not exceeding 40 newtons per millimeter squared, um, multiply VC by the FCU that you have divided by 25 exponent 1/3. All right. So we see where this thing plays a role, but just take a note. For FCU not exceeding 40 newtons per millimeter squared, whenever we find the VC, which is the design concrete shear stress, we should multiply that value by FCU over 25 exponent 1/3. Then that will give us the VC for that particular FCU. Okay, please. Very important, right? So let's look at an example or some series of examples so that we appreciate what is happening. So let's say I have a beam. And then the beam has some loads on it. Okay. Maybe let's say two sets of loads. Okay. Okay. I think it's better if I change the color so that so the top is the live load, and then what is happening to my screen? Okay, I give up. Just give me a second. So let's see if it works around this time around. Okay, great. And then the GK, which so this is this is let me hide this guy. Okay. So this is for the live load or the imposed load. And then this one here is for the dead load. Please take note. Okay. So back to our beam. For the center of the support to the center of the other support is 6 meters. Okay. The width of the support, let's say they are 225 millimeters. Okay. 225 millimeters. And so there's a cross section. Let me put that here. Okay. So we have a number of bars. So let's say let's put the bars in here. So that's a longitudinal reinforcement. How many are they? Okay, 4. 4 of these. The D is equal to these what? 547 millimeters. The B is 325 millimeters. And the area of steel that we need is 1960 millimeters squared. which could be the same as 4H25. So the diameter of one is 25 millimeters. Our FCU is 25 newtons per millimeter squared. And the FY is what? Do I have that over here somewhere? It's 500. Okay, newtons. Either FY or FYV is the same thing. All right. So these are the parameters. All right. And so GK is given as 10 kilonewtons per meter. All right. So the question says design design shear reinforcement. Okay. All right, so let's look at how we do it. So let's start with example. Let's start with one. All right. So here we'll vary the QK. We'll just vary the life load, just see how things are going to work. So the first case, QK is equal to, let's say 0, right? Let's start with that one. So QK is 0. So if QK is 0, the ultimate load W is 1.4 GK plus 1.6 QK. So that will be equal to 1.4 times 10. All right. So this will give us 14 40 kilonewtons per meter. All right. And this is simply supported beam. Okay. So if you take your beam, I'm having a hard time trying to get the span to work. So, okay. So if you have, so this is your beam, you have a load, a UGL on it. And that UGL is 14 kilonewtons per meter. When you draw your shear force diagram, this is how the shear force diagram will look like. The top value here being 42 and that being 42. So this is your shear force diagram. All right. Don't worry about there's so many things we can look at, but let's for now we're just focusing on the fact that these shear values are acting somewhere here, right at the middle point of the column. Right. That there are other things that we'll look at later, but this just to explain the concept to us. I mean, just 5 reactions, RA plus RB is equal to 14 times this length here is 6 meters. So find RA plus RB, then you find RA. And once you find RA, you can draw your shear force diagram, and that will be this value. All right. Okay. So I can put here that and the ultimate shear force is equal to V, which will give us 42, sorry, kilonewtons. All right, so let's just take a note of that. So now let's find the shear stress due to the shear force. So this will give us 42 times 10 exponent 3 divided by 325, which is the B, times 547. That's the D. And this will give us 0.24 newtons per millimeter squared. Okay. I think I jumped something, so let me put that inside here. Very important. I don't have to jump it. Okay. We have to find the VC, which is the concrete shear stress. So to find VC, we need to first know our 100 AS. So 100 AS over BD will be equal to 100. We saw that the AS, which is the area of steel, was 1960. So times 1960 divided by 325 times a D of 547. So this will give us 1.10. All right. We also know what D is. D is 547. So what do? We come to this table. Let me use the Euro code to table 3.8. Okay, sorry, the BS code, sorry. So go to table 3.8 BS 8110. Right. So you come to table 3.8. We have to find VC, right? Our effective depth is 547. So 547 is greater than 400. So from here, anything greater than anything higher than 400 will lie in the space. So I got 1.1. So I have 1 point. So what I had, well, let me just copy this and bring it down, and then maybe that will help us. So that once I just show you guys how all these calculations are done. Okay. So let's put it here. Great. Okay. So D D is 547, which is greater than 400. All right. So it means that we will be looking at values in this sector. Okay. Then our 100 AS over BD is 1.1. Okay. Now, if you come here, we have 1 and we have 1.5. We don't have 1.1. So it means that somewhere in here is 1.1. So you have to use interpolation to find it. Okay. And so our VC here will be 1 plus, it's quite an interesting concept. Let me see if I can get it right. X and Y. So 1 plus so I think is let me see if I can get it here. I don't have a calculator, so hopefully I get my answer right. So you got 1 minus 1.5 over. So you choose these values to oops, let me choose a different color. So you choose these values here, 0.63 and 0.72. So let's see 0.63 minus 0. Okay, I think I'm making it. Let me do the corrections. Okay, so it's 0.63 rather. All right, plus 1 over 1 minus. Okay, so I think I have it here now. 1 minus 1.0. Pen is messing up. Okay. 0.0, then 1 minus 1.5 times 0.63 minus 0.72. Let me cross-check this quickly. All right, so I think this should be the correct thing. All right, so normally your y is equal to y1 plus bracket open y2 minus y1 x2 minus x1, then x minus x1. So this is the equation, right? I think this should be correct to some extent. So this then will give us a VC value of 0.65 newtons per millimeter squared. Okay. And this is very important to us because that's how we're able to determine whether we need nominal reinforcement or otherwise. Okay. So now we compare V and VC. All right. So here I have my V. My V is 0.24 newtons. My VC is 0.65 newtons. All right. So yeah, we see that our V is less than 0.5 VC. Okay. All right. So if V is less than 0.5 VC, then it means that no reinforcement. So no links or no shear links required or needed. Okay. Take a note, 0.5 VC is supposed to be what? 0.325. All right. So 0.24 is still less than 0.325. Okay. So this is pretty much how shear is calculated. All right. So that's for I. Now let's look at II. So we're just going to be changing QK. All right. So now let's change QK to when QK is 10 kilonewtons per meter. So if QK is 10 kilonewtons per meter, it means that our ultimate load W will be 1.4 times 10 plus 1.6 times 10. All right. And this should give us 30 kilonewtons per meter. Okay. So again, we come back, we have this beam, we have this load, which is 30 kilonewtons per meter. So draw a shear force diagram, which takes the shape. Okay. The highest shear is 90. Right, so V, which is the highest shear, is 90 kilonewtons. All right. Now let's find the shear stress V. So that's going to be big V over BD. And so it's 90 times 10 exponent 3 over 325 times 547. All right. So this will give us 0.51. All right. So again, so yes, we compare V and VC. All right. So let's see where V lies. Okay. From here, our V is more than 0.5 VC. Okay. And V is less than VC plus 0.4. So let me put in some numbers here so that we see. Okay. All right. So this is what 0.325 is less than 0.51, which is less than 1.05. All right. So if that is the case, we go to, so let me label this table 3.7. So we go to table 3.7, right? From the BS 8110. And it states that if our V, our shear stress lies within the two parameters, then that becomes our option 2. So with our option 2, we need to provide nominal shear links, all right? So option 2 states that would provide nominal, okay, nominal shear links or stirrups, okay? So here you have to find ASV over SV, and the equation for nominal is 0.4B over 0.87 FYV. Okay. So this equation here will be 0.4 times 325 over 0.87 FYV was given to us as 500. So ASV over SV will be 0.299. Okay. So we need a table to help us. I didn't bring that table earlier, but I think now is the right time to bring that table. Okay. You don't really find that table. I've not seen the table in the code, but it's an easy to formulate table, right? So let me just pull that table up. And then let's see how useful it might be to us. So just give me a second. Let me bring it up. So this is a table which you'll be coming back to every now and then. All right. So when we calculated, our ASV was 0.299, which is roughly 0.3. Okay. And then the code says that our spacing SV should not be more than 0.75D. Okay, it should not be more than that. So 0.75D will be equal to 410 millimeters. Okay, so we cannot choose a spacing more than 410 millimeters for any of them. Okay. So we come into this table. Let's say our bar diameter is 8. So H8, which is bar diameter. Okay. Which means that what this means is that we are looking at this section right here, this space. So we need to choose an ASV over SV value more than the 0.299 that we had. And closest I can choose is this right here. Oops. Okay. So I can choose this. So I can choose a 0.0335, and this corresponds to a spacing of 300. So I can just write, okay, then we should provide H8. So the type of rebar is H because of the fact that the yield strength is 500 newtons per millimeter squared. So provide H8 um, at 300 millimeter centers. Okay. So the 300 here is the one over here. And then once I do that, it means that my new ASV over SV will now become 0.335. It wouldn't be what I calculated for earlier. It becomes what I have after choosing the spacing and then the rebar to go in for. Okay. So that's example 2. Now let's play around with example. Let's example 3, or maybe the third option. So 1, 2, I. So here again, QK, let's say is 29 kilonewtons per meter. So here I'll jump a few steps, okay, because pretty much all that we have is the same. Okay, so here our W will still be 1.4 times 10 plus 1.6 times 29, and that'll give us 60.4 kilonewtons per meter. When you find your maximum shear force, which is WL over 2, that will give us 181.2 kilonewtons. All right. So if this is a shear force, this is maximum shear force, okay, or ultimate shear force. Then it means that the shear stress V will be big V over BD. And we know the parameters, so this will be 1.02 newtons per millimeter squared. All right, so now compare whatever we had earlier, and you realize that it is the same. All right. So I can just pretty much pick every information here and just paste it right here. So I can just paste it in the space and nothing has changed. All right. Okay. So if you compare here, our V is not 0.5. Our V is actually 1.02, which still lies between 0.5 VC and then VC plus 0.4. All right. So because it's lying within that, we still need nominal, what's the name? Reinforcement, right? And this is, so it's more or less the same thing being done. Okay. So I will still end up with provide H8 at when I get earlier at 300, okay, millimeter centers. Okay, great. And then pretty much your ASV by SV provided will be what we had earlier, which is the 0.335. Okay. Now let's look at the fourth example. All right, where our live load QK is 45 kilonewtons per meter. Okay, great. So if that is the case, then our ultimate load W will be equal to 1.4 times 10 plus 1.6 times 45. And this should give us 86 kilonewtons per meter. Okay. And this means that if we find our maximum shear force V, that will be equal to 258 kilonewtons, right? Okay. And then our shear stress V will be equal to big V over BD, and that will be equal to 1.45 newtons per millimeter squared. So let's compare this, all right? Our VC plus 0.4 gave us 1.05, all right? Which means that our V is more than VC plus 0.4, okay? So once V is more than VC plus 0.4, we need to check that our V is not exceeding either 5 newtons per millimeter squared or 0.8 square root of FCU. Very important. Okay. So we choose the minimum of this. All right. And we know that 0.8 square root of FCU will be 0.8 square root of 25, which is our FCU from the question. So 25, that will give us 4 newtons per millimeter squared. So V cannot be more than 4, which is fine because V is 1.45. So far everything has checked out, right? When V is more than the limiting value, it means that we have to do a few more things. So here, since since our V is more than VC plus 0.4, it means that our ASV over SV will become the third equation, which is B into bracket V minus VC over 0.87 FYV. So this becomes a B, which is 325, 1.45 minus our VC was 0.65, okay? So all of this divided by 0.87 times 500. So this will give us 0.598. Okay, so again, from the table above, table 3.13, so this table that we're looking at, so this table right here, since we are using size 8 bar, it means that for the third option, we had 5.9. So we would prefer to go with a higher value, which is 0.67. So what this simply means is that we are to provide H8 at a spacing of 150 millimeters center or centers, where our new ASV over SV being equal to 0.671. That's what it means, all right? Normally, where you have the case whereby you need to actually provide shear reinforcement, It is not really for the entire length of the beam, right? Because if you take a critical look at shear force, right, you'll realize that for like this shear force diagram, you realize that shear, the shear is higher towards the ends. Okay, so shear higher, um, higher towards supports. Let me put it this way. But then when you go towards the mid span, the shear is lower. All right. So you don't need to have the same shear lengths throughout um, throughout the length of the what's the name? The the beam. All right. You just need a shear length for just where the shear can be high. All right. So that's the idea. Um, so with that, what sometimes we do is to find the region where you need to actually provide a shear length and then the region where you need to provide nominal. All right. So in this region here, you may need to these two regions, we may need just nominal. Okay. So with nominal, we are assuming that our VC, sorry, our V, not VC. My eraser is not erasing. Okay, maybe this time around it works. Okay. So our V, small letter V, sorry. Okay, so our V is less than VC plus 0.4. Okay, that's for the nominal. But when we provide actual shear links, like in this case here, so we need to provide or design shear links, right? Because in the end, we still provide shear links. So when we design shear links or what we call stirrups, that means that our V, which is the shear stress, is more than VC plus 0.4. Okay. So what this means is that how do we identify how far we should go? All right. So let me call this distance S. How do we identify how far we should go? And there are a number of approaches that can be used. All right. So we'll look at the first approach. Then when I solve other questions, the second or third approach can come into play. Okay. So I'm going to draw the shear force diagram. But this time around, I will not use the shear force, but I'll use the shear stress. Okay. From our calculations, with this particular question, the shear stress, where the shear force is maximum, is 1.45. 1.45. So this is for this, let me call it a shear stress diagram. Okay. Just to explain the concept. Uh, Now, at some distance, we don't know what that distance is because we're assuming that the system is symmetrical. So we need to find the shear stress over here such that beyond this towards the center, we need only nominal reinforcement. So how do we find that value? All right. That value here, let me just show with the blue. This value here typically should be equal to VC plus 0.4. Okay. So it becomes like the boundary. If you go towards the right, In this case, if you go towards the right, or if you go towards the center, then you are using nominal. If you go towards the supports, then you are designing for the shear links. All right. Okay. So I think we found this answer to be 1.05. Right. So here's 1.05. Okay. Now let me just add something, or let me just redraw and let's see. So this point be my center for now, just so that I'm just trying to exaggerate things. So here, this is the center. Okay, the center over here. Please take a note. This is 145. We have here 1.05. The distance from the center to the edge is half of the 6 meters, so that becomes 3 meters. Now we need to find this distance. Let me call this distance x. Okay. So this is x, and then from here to here will be the s. Okay. So using similar triangles, we can see that 3 over 1.45 will be equal to x over 1.05. So let's find x. When we find x, so our x is equal to 2.172 for x, which means that we can determine what the s value would be. All right. Do I have it somewhere here? I'm hoping I have it somewhere. So let me quickly calculate it, and then I put the value in there. So it means that my s here will be 3 minus 2.172. So let's say 3 minus 2.172. So that'll give me 0.828 meters, or 828 millimeters. Okay. So pretty much this distance here, this distance here, the 828 millimeters, has some few things interfering. So this distance here is where we design the shear links. Okay. So that will be this zone right here. So that'll be this zone over here. Okay. Then the zone on the right will be for the nominal. Okay. So let's find how many rebars we need for that zone. And then to find the number of rebars that we need for that zone, in that zone, we said that we should use H8 at 150 millimeter center. So that's the spacing between the stirrups. So if I want to know the number of stirrups that I need, I'll divide the length. So I'll divide S by 150. So it's more or less like dividing S by SV, more or less. So it becomes 828. So it's usually 1 plus, if you want to know the number of rebars, is 1 plus. So let's say the number of rebars is always 1 plus S over SV. Okay. So this should give me 1 plus 828 over 150 And I think that should give me what, 6 point something. Let's say 6.5 something, I'm sure. Um, so let's say 828 divided by 150. Yeah, so 6.52. Okay. So since it's 6.52, then we have to approximate it to the next the nearest whole number, which is 7. So pretty much for that zone, we need 7, not again, we need 7H8, okay, at 150 millimeters centers. Okay. So if I'm to draw pretty much how the beam should look like in terms of the shear links arrangement, okay, I think I need space at the top. Please erase. Okay, so let's go back. Bring this down a little bit. Okay, so I think this is fine here. Okay, so let's say that I have my let's say before I did the shear, I also did my um, main beam, so we are good. Um, okay, so let me put my columns somewhere here. Let me put my column somewhere here. Okay, all right, great. Um, so this is the start point. Let's say the start point of the rebar is on the face of the column. I'll explain these things shortly. So this zone, I'm just going to color code it. This zone over here is where we actually have the shear links being designed for. So these zones, all right? So normally this is what we do. Um, I need a green color. So between this and that is where we have the 7H8 at the 150. Okay, so these two zones will have the same thing. So this is 7H8 at 150. All right. Then let me use a different color just so that we see the difference. Then in between here, I think we had the H8 at 300. All right. So in between here is for the nominal. This side is for the nominal. Okay. What it simply means is that in this area, we're only providing a minimum number of links. Okay. This is a nominal, whilst the yellow zone is the one that we need to prevent shear failure. Okay. Yeah, so let me recap. All right, so the next thing that we'll do from here is to do a proper design of a simply supported beam from scratch, where we are looking at both bending and shear, and then just look at the steps involved. All right. So let's look at an example. So with this example, I would combine um, all that we've done so far with regards to being able to design a beam for both bending and then for shear. All right. So let me try and put the question together. All right, so we have a simply supported beam, as is shown below, and the beam supports some distributed load, uniformly distributed load. And here we have a dead load of 40 kilonewtons per meter, which includes the self-weight of the beams and then all of that. Then we also have the imposed load, which is 12 kilonewtons per meter. And the material strength for concrete FCU is 30 newtons per millimeter squared. And then the steel rebar here is 460 newtons per millimeter squared. All right. The width of the beam in terms of its cross section is 300 millimeters. And then the effective depth is given to us as 550 millimeters. Then the span of the beam is 6 meters, right? And usually we take the spans, or we measure spans from the center of the support, right? So if you have a column whereby the column has a width um, of 300 millimeters, then it means that we take half of it, which is 150. So that becomes the center of the column, and that's how we measure the spans. Okay. So let's look at how to solve such a problem. So we have to design, pretty much design the beam. All right. So design the beam. That's the question. So in this case, we are designing for both bending and then for shear. All right. So let me put here solution. Okay, so this should help us in terms of the steps on how to analyze a typical beam, right? So let's start. We start with the analysis. So let me say A, the analysis. Okay. So here we try to find ultimate moment and then our ultimate shear or maximum shear. All right. So let's find the ultimate load. The ultimate load. Okay. W. Some have a U as a subscript is fine. That is 1.4 GK. So we multiply the load by their partial factors. All right. So then this will be 1.4. The G is giving us 40 um, plus 1.6 times 12. That is the imposed load. So that is the imposed load. So when you would do this calculation, we get 75.2 kilonewtons per meter. So we can take that information and then, so now like we have a beam, a simply supported beam with a UDL on it, okay, whereby it is 75.2 kilonewtons per meter, right? So here, our maximum design moment, or the ultimate design moment. So let me put it here, the ultimate uh, let me just redraw all of that. Okay. So the maximum design moment that is uh, I can't get my eraser to work. Um, okay, so the maximum design moment M is equal to WL squared over 8. So it becomes 75 uh, 75.2 times C squared over 8. And this should give us 338 kilonewton meter. So this becomes our maximum moment that would experience in the beam, which for a simply supported beam, your maximum moment um, is at the midspan. All right. So let's deal with the moment for now. We'll come back and look at the shear. All right. So once we find the maximum moment, so the next point, which will be B, will be the bending reinforcement. Okay. So here we have to find K, where K is equal to M over BD squared FCU, BD squared. So K is equal to M over BD squared FCU. Okay. Increase the thickness of my pen. Okay. So let me do the correction. So BD squared FCU, which then is 338 times 10 exponent 6, trying to convert everything to newtons and then millimeters. So the B is 300. The D, it was given to us as 550. Then times an FCU of 30. So this gives us a K value of 0.124. Great. So we need to compare the K. So compare with K prime. All right, where K prime is 0.156. So since K is less than K prime, then it means that we only need singly reinforced. All right. So we are going with a singly reinforced um, steel rebar. All right. So if K is less than this, we are good to go. Now we find Z, the lever arm, and we know that Z is equal to D. What's my equation? So D bracket open 0.5 plus square root of 0.25 minus K over 0.9. All right. So once we know the value of K, where K is 0.4, we'll end up with our Z value being approximately 456 millimeters. Okay. So the area of steel required, M or AS, is equal to M over 0.87 FYZ. So that this becomes 338 times 10 exponent 6 divided by 0.87. And our Fy was 460. All right, times a Z value of 456. So this should be approximately 1855, and not 58, 1855 millimeter squared. All right. So So this is the area of, let me put it to brackets. All right, so once we have that, now let's continue with our calculations. We have the area of steel required, but we also need to know the number of rebars that we need. So let's say we choose rebar of diameter 25. All right, so let's say 25 m. So for 25 m, your I think the area uh, for one would be so you can quickly find the area 25 squared times pi divided by 4. I think it's roughly about 500. I'm just estimating to be about 500 millimeter squared. So that's the area of one bar. So it means that if I want to know the number of bars that I need, then it's going to be 1855 divided by 500. So this should give us 3.71. All right. And since 3.71 is not a whole number, then it means I have to run it up to the nearest whole number, which is 4. So I need 4 number of the rebars. So in the end, I'm going to use 4T, where T here stands for the type of rebar. And since this is a 460 Newton per millimeter yield strength rebar, which is the high yield steel, the the nomenclature or the naming for that is T. So it's 4T25. Okay. And the area of 4 number 25 diameter rebar, that area would be so it becomes 500 times 4. So roughly about, let's say, 2000 millimeter squared. Okay. So if you had to draw that, if this is your cross section, it means that here at the base you have 4. Okay. So this is 4T25. So pretty much we are done with the portion for the bending check. All right. So this is here is quite important. This is important. If after calculating K and K is more than 0.156, it means that you need compression reinforcement. So the computations will slightly vary from what you've done so far, right? With this example, per the value of K, we only need, what's the name? We only need tension reinforcements. Okay. Let me just make sure that the recording is ongoing. All right. So now let's go to the so okay, let me go up here and then just draw the rebar. Okay. So in effect, this is how the rebar looks like. Okay. And normally when you have your rebar, so this is your 4T25. Maybe let's say you can even add B or B1 because it's at the bottom, right? Sometimes when you are putting together this rebar arrangement, usually where the so let me put that on the side over here. Usually where the beams and then the columns overlap, because you have your rebar going through and also have, I mean, the rebar from the beams going through, also you have rebars from the columns coming through. There is a lot of congestion at that junction or that joint. Once there's a conjunction of rebars, your concrete is likely not to be placed properly over there. Okay. And again, tension reinforcements at the bottom are for the spans. They're typically not for the supports. So we can sometimes, or generally, we curtail how much of the rebar gets to the supports. Okay, so I'm going to write that over here. So sometimes, SOME, sometimes we curtail uh, the number of rebars going to the support. So if I'm to draw my beam again, just so that I explain that, so this is just on the side. If I'm to draw my beam again, I have my rebar right here, and I still have my columns at the ends this way. So I have my columns right here. This is fine. I can, so I'm putting this line over here. It's just to show that, so let me just add a little bit of color. Okay. So not all the four will go to the support. So what it means is that um, somewhere in the spans you have 40, 25, but as you go closer to the supports in this space, it becomes to, let's say only half of it goes. It becomes T2, T25, and only half also goes. It becomes to T25. So from the span or from the mid span at the base, you have four, right? So it means that if you cut a section through here, let me call it section 1, 1. You cut a section 3 and section 2, 2. For section 1, 1, you have 1, 2, 3, 4. Right. Then for section 2, 2, depending on how you curtail, you might end up with just 2. So it means that the middle portion does not go all the way to the end of the bar. Right. And there are engineering reasons and also construction reasons why we have that. Okay. So let's say that half of it goes to the support. We'll come back to why I'm spending time on this. All right, so let's look at the next sets of steps. So now let's look at the design for shear. That is, so the first one was for the design for bending. All right. So let's look at A. So that'll be the analysis. So for the analysis, we are looking at finding the maximum shear. I didn't draw the bending moment diagram because I assume we cannot draw it. This will be our bending moment diagram. Okay. With the value here being 75.2 kilonewton meter. Sorry, no. It wouldn't be that. The value would be 338 kilonewton meter. Okay. So the maximum shear force V, wrong pen, V will be equal to WL over 2. So that'll be the 75.2 times 6 over 2. All right. And then that would give us, do I have that information anywhere? That'll give us, I think 225.5 kilonewtons. Okay, so let us draw the shear force diagram. So our shear force diagram will look like this. So these are center measurements. So this is supposed to be 6 meters. All right. So the value over here is 225.5 and then 225. Yeah, 0.5 kilonewtons. Great. So what do we do next? The first thing is to find the maximum shear force. So take you through a few steps. And so this is A, B. We need to find what we call the maximum shear stress, which is from the maximum shear force. All right. So maximum shear stress. All right. And then we know that the maximum shear stress, V, is equal to the shear force, Vs. I'll explain what Vs is, where um, the shear force, Vs, is shear force at the face of the support. So at the face of the support. Okay. When we're looking at shear force or shear stresses and being able to come up with shear reinforcement, we realize that normally when it comes to shear failure, okay, if this is your column, you'd realize that, or from what we discussed, this is the direction of shear, right? I mean, diagonal tension failure or diagonal shear failure. It occurs from the face of the support towards some loading, right? Or typically up to a distance of D, all right, where D is effective depth. Okay. So even though shear max, let me choose a different color. Even though shear max would occur, so our 22.5, sorry, is occurring at the center point of the support. We are actually interested in the shear that is occurring at the face of the support, because usually that's where failure starts from. All right. And this also helps us not to over exaggerate the shear stress, right? Because once you exaggerate the shear stress, it means that you would also have to increase what's the name? The shear reinforcement that you have to place in there, which would also lead to a high cost of construction. All right. So now let's find the shear force at the face of the support. So that shear force Vs will be equal to, so you're looking at, so let me use this marker here. So you're looking at shear at this point. So if we know this distance here, which will be half of the width of the column, that is 150 millimeters, we can easily determine what Vs will be. All right. So using the shear force calculations, Vs will be equal to 225.5, which is the shear force at the center point. Sorry, I mean the midpoints of the support, right, at the far end, minus the ultimate load times the distance, which is 0.15. All right. So if we do that, this will become 225.5 minus 75.2 times 0.15, and this will be 214 kilonewtons, or approximately 214 kilonewtons. And this is the shear force at the face of the support. So the maximum shear stress V, or small letter V, will be 214. Let's convert everything to newtons. So times 10 exponent 3 divided by B is 300, and D is 550. So that'll give us a shear stress of 1.3 newtons per millimeter squared. Okay. And we need to compare to the maximum, right? This cannot be greater than the minimum of uh, either 5 newtons per millimeter squared or 0.8 square roots of FCU. Okay, so this will be 0.8. Our FCU is 30. So 0.8 times the square root of 30 uh, will give us 4.38 newtons per millimeter squared. Okay, so we choose the smaller value to compare with our V. All right. So once our V is less than, or it's not greater than 0.8 square root of FCU, we are good. It means that failure will not be governed by diagonal compression failure, which is what we don't want. All right. Okay. So that's something to take a note of. And the code stipulates that all our maximum shear stresses should be below these values. The moment they are higher than these values, then we have to go back and then see how we can alter the dimensions um, of our beam. All right, we have not done much on how to uh, decide on the size of beams. So we'll do that going forward. But for now, this is what we do. V, or the maximum shear stress, should not be below um, zero. I mean, 0.8 square root of FCU. Should not be higher, sorry, than 0.8 square root of FCU. Okay. So once we find the maximum shear stress, what do we do? The next steps is to look at the shear links, right? See if we will even need shear links or not. All right. So let's look at how to find shear links. Now let's find the concrete stress, or the maximum, what's the name? Shear stress in the concrete. Oh, sorry. All right. So let's find the VC, which is the design concrete shear stress. Okay. And that we get that from the table. I think last week I showed you. As part of this lecture, I showed you a similar table. I'll bring it up again so that we see what the table is. All right. So to find the design shear stress for concrete VC, we need D and also 100 AS over BD. Okay. So let's look at see if I can get the table. Okay. So and the AS over here is the AS at the section we are looking at. Okay. So remember I mentioned that as we're going towards the support, we reduce the number of rebars which are going towards the support. So we're assuming that at that point, our rebars are no longer 4, but actually 2. So it's now 2. So we have 2T25 at the supports. All right. Okay. So what this means is that my AS will actually be half of what I had. Right. So I think so it becomes 100 AS over BD. I'll do some approximations over here so that it makes the whole thing simple. So it becomes 100 times 1,000. All right, so these two T will give me 1,000 millimeter squared. All right, over B, where the B is 300, times a D of 550. This should give me approximately, you might get a different answer if you calculate. It's fine. You can work with your answer. Um, I don't want to spend too much time on that. So this should be roughly about 0.59. I think, let me just 4 seconds. All right. So 1,000 times 100 divided by 300 times 550. Okay, so it's 0.6, 0.59, 0.6 are about the same, so it's fine. Um, so if it's 0.59 and then our D effective depth is 550, which is more than 400, then it means that we are dealing with the zone right here. And please take notes, your FCU is very important. There are different types of this table, or there are variations of this table, and this one is based on an FCU of 30 newtons per millimeter squared. The one I had earlier, or the one we did for the previous calculations, FCU was 25, so the table was slightly different. There's a way to quickly um, 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 change the table or to find VC, all right, even if you have different compressive strength. Okay. I think whatever you find for VC, you multiply that by, don't you remember the value? I think it's FCU over 25 times 1.3 divided by, I think, 165. I'll just cross check that briefly. Um, so FCU, so this is, I'm way off. It's 1.06. All right. So this table has the multiplication already done. So this is for different values of VC. All right. Okay. Uh, so let's continue with our calculations or with our um, trying to find our VC. So here, um, our 100 AS over BD, it's somewhere between, so that's 0.59. So somewhere between these two values. So it means that we are looking at choosing values between 0.53 and 0.61. And I think if you go back to the previous calculations, there's an equation that we use to help us to calculate that. All right. Um, let me see if I can bring the equation up again. Right. So it means that our VC, oops, different color. Our VC would be equal to 0.50 plus this whole lot of equation. Um, no, sorry, 0.53 rather. Let me correct it. 0.53 plus 0.53 minus 0.61 over 0.5 minus 0.75 times 0.59, which is our x, minus 0.5. So this should theoretically give us 0.6 something. No, okay. Yeah, so it's 0.56 newtons per millimeter square. You can always cross-check these numbers, right? So our design strength, concrete shear stress, sorry, the VC, small letter VC is 0.56, right? So once we find that, we need to determine um, the shear strength or the shear force, sorry. So we have our VC. Now we need to find VD, which is the shear force at a distance D um, from the face of the support. Okay. So I had to explain earlier why we're doing that, because we normally we where's the drawing, and there goes the screen. Okay, so normally the crack. This is so frustrating sometimes. Where are you? Okay. Usually, this is the direction of the crack, and then we believe that this zone here is our critical zone. All right. I mean, from this zone going is our critical zone. So we want to find the shear at a distance d from the face of the support, because we believe that typically that is likely to be the length, the horizontal length of our crack development, all right, our diagonal cracks. Okay. Um, so let's find the shear VD. So VD can easily be found just the way we dealt with the VS, which is the shear from the face of the um, support. So VD is simply VS minus WD. All right. So this is 214 oops, minus 75.2 times 0.55 for D. And this should give us 173 kilonewtons. All right. So we use that to find the shear stress. Right. So here our V will be VD, V sub VD times, or divided by BD. And that'll be 173 times 10 exponent 3 divided by B of 300 times a D of 550. And this should give us 105 newtons per millimeter squared. Great. All right. So to find the shear links, we need to compare this value right here and then the VC. We compared it to. All right. And we had a table. I'll just bring that table here again so that we always have something to refer to. Um, so I'm going to pull a table up here. Great. It should show. Yeah, it's here. So we have these options to go through and then just check which one will be appropriate for what we are doing. All right. So usually this is what I do on the side. I find 0.5 So let me do that on the side so that it doesn't interfere with what I'm doing. So I find 0.5 VC, right? And our VC is 0.56, all right? So 0.5 of that will actually be very small, which means that 0.28, and definitely our V is more than that. Okay. Now the next thing is to look at VC plus 0.4. All right. So that will be 0.56 plus 0.4, and this will give us 0.96. And again, it means that our V is more than 0.96, which means that the only option we have to deal with is the third option. All right. So with the third option, we need to design shear links. And here is the equation to design the shear links. All right. So it means that we need to find ASV over SV, which will be equal to BV minus VC over 0.87 FYV. So our B is 300, our V is 1.05, our VC is 0.56. All right, divided by 0.87. And our FYV is the same as the one we had as 460. So we put that over here. And this should give us 0.68. All right. So once we have 0.68, so it means that ASV over SV is equal to 0.68. So let's say we are using okay, so let me change something over here. So instead of 460, rather, uh, let's do it this way. Let's make the FYV 250. All right, so it means that we are using mild steel. So let me put it over here. So yeah, okay, so then put FYV is 250 newtons per millimeter squared. So that is mild steel. Let's work with that because that one is normally you find that in most residential buildings, this is what happens. The shear links are typically made of mild steel. So this will give me 0.68. Let's say we are using bar of diameter 10. All right, 10 mm. All right. So if you want to find, so you can use a table as we did in the previous example to find ASV, or I always find the table easier, or we can go through some series of calculations to arrive at that. So if we are to use the table, I'm going to bring the table again. So I'm just trying to show us how all of these things are done. Okay, so the table should appear. It's going to take a little second or two. Okay, so finally the table is here. All right. So if the table is here, we had an ASV SV of 0.68, where ASV is the area of the tension, sorry, area of the shear reinforcement. And these are two legs, okay? And then the SV is the spacing between the reinforcement. So what do? So we go through it. So we come here, since we're using a bar of diameter 8, our options are limited to this line, okay? And then the highest spacing or the SV should not exceed 0.75D, right? So it shouldn't be more than 75% of the D, all right? This is to make sure that you have at least one of your your shear rebars crossing the cracks, assuming cracks are supposed to be forming, all right? So so this should be 412.5 millimeters. So we cannot have spacing more than this. All right. So here, what did I go with? Let me just see what I went with. Um, so let's choose this option here, right, which is 0.98. So we choose 225. So it means that we use R10. So let's say R10 links at a spacing of 225 millimeters. Okay, centers. And then our new ASV over SV would be 0.698. Works perfect. All right. So once we have that in place, we this shelling, the R10 doesn't go the entire length of the beam, right? It goes up to a certain point where shear is critical, all right? Because there are some parts of the beam that shear doesn't really play the significant role in terms of the failure that is likely to occur, especially towards midspan. Towards support, shear is critical. Towards midspan, bending is critical. All right. So what it means is that you would want to have more shear reinforcement towards the support than towards the center. Right. Okay. So before we go that, let me just add a last bit of it. Let's do the typical nominal, what's the name? So let's do the nominal links. All right. And for the nominal links, we are told that um, it is ASV over SV being equal to 0.4 B divided by 0.87 FYV. All right. And we know what B is, so it becomes 0.4 times 300 over 0.87 times FYV of 250, and that should give us 0.55. Okay. So again, using the same R10, I can come in here, which means that the most appropriate value to use for this case here will be for phenomenal links is R10 at a spacing of what 275 millimeters, right? Where the ASV over SV is 0.571. Okay. Okay. So this is for the nominal links. All right. Again, where does a nominal link start from and where does it end and all of that? So we have to do a bit of calculations here and there to understand how that goes. So I'll call this point E. Oops, supposed to be black. E. And let's look for the extent of the shear links, right? That would also help us to know um, the extent of the nominal links anyways. So let me come back here. Okay. There are two ways to do this. So I'm going to explain the two methods. You can choose which one you would want to go with. So this is my shear force diagram. Okay. This looks a bit funny, but I think we get an idea. Okay. So, I mean, um, so when we found, so I'm looking for right now I'm comparing shear stresses, okay? Not the shear force. I'm just comparing shear stresses. I'll compare the shear force later. We know that at the top, we got 1.3 Then at a distance D from the face of the support, we had 1.05. All right. Now, if you are dealing with nominal lengths, what this means is that your for nominal lengths, I think I need to create a bit more space. So let me just move this guy here uh, down a little bit. Does it work? Yeah, it works. Okay. So normally when you're dealing with nominal links, you might need a V, where this V is simply VC plus 0.4, because that's the highest level you need for you to do nominal links, right? If you come back to this table, here is for the nominal links. So the highest value for the shear stress, V, coming from the load, can only be the shear stress in the concrete plus 0.4. Okay. So if we do that, this becomes 0.96, which I've already written. So it means that there's some point here. So this is zero. There's some point over here where we have 0.96. All right. So let's call this distance here x. All right. So at what point, what this means is that if we can find x, then that will help us to know the extent of our shear links. All right. So here you can apply similar triangles. Um, so let me write this value. Let me just put some little bubbles around them. So this is for the face of supports. All right. And then let me change this color. Maybe. Then this guy here is at a distance D from the support face. All right. So what that means is that from this point towards the center, the entire span of the beam is 6 meters. So half of that will be 3. So it becomes 3 minus 0.15, which is coming from the half the width of the column, because your 1.3 shear stress is starting from the face of the support. All right. So quickly, um, using the principle of similar triangles, it means that 3 minus 0.15, you can write a much more simple version, is to 1.3, whilst x s is to 0.96, right? So here, if we are to make x the subject, then x is equal to 2.105 meters, which is the same as 2105 millimeters. Okay, all right. So if we have that, we can use that information to find our spacing. We'll come back. So we can use this option to find x, or let me just, so the or is important, one of the two. So this case is the same thing I'm drawing here, all right? The shear force at the face of the support was 214. All right, we found that one, that one. And then the shear force at a distance D, so this is your D, we found that one to be, what did we get? And then we're gonna go up. We got 173. Okay. Now we need to find the shear, which we call the Vn, where the Vn is the um, shear resistance of both the nominal links and then the concrete. All right. Vn will correspond to the 0.96. All right. So let me just put over here. Vn will correspond to yeah, sometimes so small v of 0.96, right? And we have written that Vn is equal to uh, bracket open ASV over SV times 0.87 FYV plus BVC times D. All right. So let's put that. What was our ASV? Um, which one? Let me make sure I'm using the right ASV. All right. So for the nominal links, my ASV was 0.55 and I chose 0. So I chose 0.571. So it becomes, you have slight differences from my answer, it's fine because I'm doing a lot of approximation. So 0.7, 0.757 times 0.871 times 250 plus B of 300 and a VC of 0.56, right, from the concrete that we found earlier. Then a D of 550 will give me a Vn of roughly 159 kilonewtons. Okay. So that's one way to find a Vn. So I think my all statement should not even be here. It should be more of below, sorry. Okay. Okay. I can just put that information over here. So the other way, so this is one way to find Vn. The other way to find Vn would be to use the information above, where here Vn corresponds to this distance. We found x, so we know what Vn is. Vn corresponds to, sorry, let me get my x straight. I got my x wrong. Let me put the x in the right position, sorry. Okay. So x should actually be here, okay. X should rather be here, all right. So Vn corresponds to x, which we got that to be 2.105, and then 214 also corresponds to 3 minus 0.15, which is the same as 2.85. All right. So let me move things around a little bit. See how things pan out. Okay, so I think this is fine. So what this means is that, let me just open this box and then add some small information to it. So it means if I'm comparing the two, then 2.85 over 214 will be equal to 2.105 over Vn. All right. And then if you make Vn the subject over here, your Vn will be approximately 158 kilonewtons, which pretty much is the same as what we have in the space. All right. So you can either use one or the other and you still get your Vn. Okay. So once we get our Vn, coming back here, so from the face of the support, to where the nominal link starts will be the extent of the shear length. So here, x is supposed to be the extent of the shear links. So again, you can use a number of ways to calculate for that. So you can calculate for that using a number of ways. So one of them would just be to use the values as you have them. So simply S will be equal to, so this will give me 2.85. So S will be equal to 2.85 minus X. All right. So it becomes 2.85 minus 2.105. And this should give me 0.75 or approximately 0.75 meters. All right. So you can use the values or the distances to find S, or um, you can also use the shear forces to find S, right? So for example, here will be your S again. All right. So uh, S there will be equal to Vs or Vn, depending on what you want, minus Vn all over W. And this will still give us 0.75. Okay. But so this is the same as 214 minus 159 over 75.2. Okay. So this is the extent of the shear links, which means that our shear links would have to be in this zone. All right. So this is for the shear links, and then our nominal links will be in this zone. Okay. So whatever is happening, sorry, let me just take this one back. So whatever is happening on the left side, the same thing is happening on the right. Okay, so this is for nominal. Okay. So then the information here is for the shear links. Great. So now let's see how many do we need, right? At least we have said that for the shear links, we are using 10R, 10R links at a spacing of, I think, what did we get for the spacing? 225 maybe? Yeah, 225. Okay. And then for the nominal links, it is 10R at 275. So this is the information that we have. But now the question is, how many of these do we need? All right. So we know the extent of the shear links, that it can only cover 750 meters or 750 millimeters. All right. So if we want to find the total number, so for this, if we want to know the um, number of shear links, this is how we go about it. So it is 1 plus S over the SV, which is the spacing. All right. So in this case, it's going to be 1 plus 750 over 225. And this would give us, my calculator, let me see, 750 divided by 225 plus 1. That'll give us 4.33. So approximately we need 5. Okay. So it means that for the shear links is 5. Oh, what? It's supposed to write it R10, not 10R. Sorry. A mistake on my side. So this is supposed to be R10. R10. All right. So this becomes 5R10 links at 225. So that'll be for the left side. Um, so let me see if okay. So if I'm to um, draw how the shellings will be positioned. So this is my uh, beam nicely with my column supports beneath it. Okay. So I have my beam, my main rebar. Let's say we have some rebars here. All right. Okay. So the shear link starts at the face of the support right here, and it expands up to some distance of 750 millimeters. Okay, so I mean whatever is happening on the left also happening on the right, so it's a mirror image. So we have this distance right here, okay, where we are putting 5R10 at 225. Okay. So 5R10 at 225. Okay. Then in between, we have the nominal links, which might start from some distance away. So here, this zone here would be the nominal links. Okay, so this is the nominal links, and that would be R10 at 275. If you want to find the number of nominal links that we have, we can easily um, determine this distance. All right. The space between the start of the nominal and then the share, this distance would be the 225 because that is what's coming from the share links. All right. So we can easily find this distance, let's say LN, and then determine how many we need. All right. So I think that should be about it for this question. I would, I think that's about it. Just go through it. If you have any questions, we'll touch base on whatever questions you have. All right. Thank you and enjoy the rest of your day.